So welcome to my master's thesis presentation, Forest Structural Code Editing with Multiple Cursors. So in their daily work, developers sometimes need to perform repetitive edits, but manually performing these edits is time consuming, and so it's important to automate them. There are various tools that can help to automate repetitive edits, but not every tool is suited for every task. Additionally, some tools are more interactive than others, and I'd like to show this on an example. So here we have a LaTeX table, which I recently needed to edit by swapping the first and last columns of the table. And performing this edit manually is clearly going to be time consuming for all 20 rows. So there are various tools to help automate this, and one of them is multi-cursor text editing, which is a feature of most text editors today. And this lets you create multiple cursors. And now every command I execute is executed by every cursor. So here I copy to that first column. Now I copy the last one, and the edit is complete. And this was a very interactive edit. I performed the edit step by step as normal, and immediately saw the changes in every repeated location. A more classic approach, which is slightly less interactive, is using macros in a text editor. So in an editor like Vim, here I'm just using a Vim mode, you can start recording a macro, and all the commands which you use are saved. And you can then replay this macro over various locations. So this is slightly less interactive because although we saw the edit step by step in one location, we only saw it applied to the other locations later. Some other approaches to performing repetitive edits are find replace with regular expressions, but as you can see in this case, that would be quite involved. Additionally, we could write a text processing script, by which I just mean a program which manipulates strings in order to perform the desired edit. However, now it becomes clear why it's important to have interactive tools, because interactive tools can be an integrated part of a normal development workflow. Developers can justify using these tools to perform a repetitive edit even in a small number of locations. So while I might use a multi-cursor text editor or a text editor with macros to perform an edit in, say, 5 locations, I wouldn't write a text processing script for that same use case. Now let's look at a more complicated edit. So here, the user wants to take this object literal, and for every value of every property in this object literal, they want to wrap it in the function called warn on error. So to manually perform this edit is not much harder than the LaTeX edit. I would just click here and type warn on error, and then click here at the end of the expression and type a closing parenthesis. However, this edit is much more difficult to automate using the tools shown here. And the reason for that is that this edit is structural in nature. So a core part of the edit is finding the range of this expression. And that's quite hard to do using text-based primitives, because the expressions can span different numbers of lines, and they're separated by a comma. However, they might also contain commas. So while performing this edit manually with a text-based tool is just fine, we need to use a structural tool in order to automate it. So a lot of structural tools are analogous to the text-based tools. We have AST-based refactoring scripts, which work with nodes of an abstract syntax tree to perform an edit. And sometimes this is done with a library, sometimes with a domain-specific language. We have structural find replace, which is the analog to find replace with regular expressions. And for text editing with macros, there's not really a widely researched analog. However, there is programming by example, where the user performs an edit in one location, and the system infers how to replay that edit in the other locations. But multi-cursor structural editors and structural editors of macros, the analogs here, have not been researched much at all. But I'd argue that this area of the chart is quite important, because in order to automate edits, which are structural in nature, and not just perform them manually, we need to use structural tools. And additionally, it's important to have interactive tools so that developers can justify using them even for small numbers of edits. And that's why we propose Forest, a multi-cursor structural editor. Now, before I get to our contributions, I'd like to just demonstrate the edit we've discussed in Forest. So here we have the same code as before, and I'm not going to explain the steps here. So that's done. So as you can see, this edit was easy to perform in Forest because it's naturally a structural edit, and Forest is a structural tool. But additionally, Forest performed the edit just as interactively as multi-cursor text editing would. So, our contributions. We built Forest, a structural editor for TypeScript. It's one of the few structural editors for languages with complex syntax, and it's the only structural editor for TypeScript and JavaScript. We then added multi-cursor features to Forest, and there's actually only one other structural editor with any multi-cursor support, which is GobCamel. And since this is an Emacs plugin, it can be combined with the Emacs multi-cursor plugin to effectively get a multi-cursor structural editor. However, there's no special integration between the multi-cursor features and the structural editing features, making Forest the only structural editor with special integration between multi-cursor and structural editing. Finally, we evaluated multi-cursors, evaluated the concept of multi-cursor structural editing in two ways. First, we took real-world refactoring scripts and tried to reproduce their edits in Forest. And additionally, we looked at real-world edits in a code base and estimated the number of them which could be performed using a multi-cursor editor, making this the only evaluation of a multi-cursor structural editor. So before I go to the multi-cursor features, I'd like to just show some of the basics of Forest. So in Forest, the program is shown as text, and the user has a cursor, which can either select an AST node, so I'm selecting leaf nodes here, or it can select a range of sibling nodes, so I'm selecting these two sibling arguments. You can also select higher level nodes like this property, or these free sibling properties. To make edits, the user can place the cursor somewhere and insert before or after it, making typical edits actually quite similar to a text editor. And additionally, there are commands like delete and copy. And in some cases, like if I delete these arguments here, Forest will reformat the whole document. So run the pretty printer. Forest actually continuously pretty prints the document. Now I'd like to discuss some multi-cursor features. And I can't cover all the features of Forest, but I'm going to focus on these three here. Splitting cursors is a feature you've actually already seen. So when I have this single cursor here, which has the list of 6 properties selected, note that I still have one cursor. I can now use the split command to get 6 cursors, 1 for each property. Now this seems like a really basic thing, but it's actually a unique feature to Forest, because in a multi-cursor text editor, you would perform the split using a character like the comma, or white space, or a regular expression. However, this has the same problems that we discussed in the introduction. Because the expressions contain commas, you can't reliably split them with such a strategy. But in Forest, this split is just naturally not a problem because it's aware of the structure of the program and can use that to perform the split. The hierarchy of cursors is another feature that's unique in Forest. And to show this one, I'll switch to a different example. Here. So what we'd like to do here is the following. I'd like to add type annotations to each of these arguments and a type annotation to the return type of the function. Now, the way I did this was I focused the argument list, split to get free cursors, appended the type annotation, and now I need to have one cursor in order to annotate the return type and not get free copies of it. So I use the reduce to first cursor command to leave only one, and then I annotate the return type. Now say you wanted to do this edit for both of these functions at the same time. The natural way to do this is first starting with one cursor at the root of the document to split this cursor. So now we have one cursor per function. And now we would perform the edit the same as before. We would split for these cursors, append type annotation, and now we would reduce the first cursor. But if we do that and end up with only this cursor here, then we'd only get a return type annotation on this function here and not on the function g. And that would be a problem. So what actually happens when you reduce the first cursor in forest is this. We're left with both of these cursors, and we can now complete the task as before. So what was happening there was the hierarchy of cursors system was being used. So when we start out with this one root cursor. And when we split it, we now have two cursors, but they're both descendants of this one root cursor. However, if we split the cursors again, we now have 6. These 3 here are descendants of the cursor that was in F, and these 3 here are descendants of another cursor, which was in G. So when you perform an operation like reduce the first cursor in forest, it considers these two groups separately based on what parents the cursors have in the hierarchy of cursors. And that's why it can perform the reduce this way, keeping both cursors. This is really important because it allows performing multi-cursor edits themselves in multiple locations. The final feature I'd like to highlight is marks with AST tracking. So back to the original example, marks are a feature which other editors also have. So what you do is you can mark a location like this, and now that I've marked it, I can, oh, sorry, did it wrong. So I'll mark this object literal, and now that I've marked it, I can jump back to that mark. And what happens if I delete a piece of code before the mark is that forest still successfully tracks it, even though its text position has changed. And some text editors might handle this case correctly. However, if I perform a different edit up here, by deleting these arguments, trigger the pretty printer, now the text position of the mark has shifted, but it hasn't shifted just because of my edit. It's shifted because the pretty printer gave a different output. And forest still correctly tracks the mark, where other editors wouldn't. So to evaluate how well forest works, we wanted to compare it with AST-based refactoring scripts. Although these scripts aren't interactive, they're the most expressive way of performing structural edits because you can write arbitrary code to perform your edit. So we collected real-world JS CodeShift scripts from GitHub. JS CodeShift is the de facto standard library for writing AST-based refactoring scripts in JavaScript. And we tried to reproduce their edits in forest, classifying whether we could or not for each script. So no means we couldn't perform this edit for some major reason, and possibly we'll never be able to perform this in forest. Maybe means we could partially perform the edit, but fully performing it requires extra manual work or potentially a new feature in forest. And yes means we could perform the whole edit, possibly with some minor limitations. So in total, we tested 48 refactoring scripts, and our results gave us 20 scripts classified no, 17 maybe, and 11 yes. Additionally, we noted all the issues we encountered while, sorry, so to clarify, we actually tried to perform the edits of all the maybe and yes scripts in forests. And we noted issues from all three kinds of scripts, but the issues from the maybe and yes scripts also include any that we encountered in practice while performing the edit. So I can't talk about all the different issues we encountered, but I'd like to focus on these two here. Have to recreate cursors multiple times is an issue which depends on the filtering system in Forest. So say we have the same situation, and we want to wrap these expressions differently depending on whether they contain function calls or not. So this expression and this expression and this expression and this expression, which contain function calls, we'd like to wrap these in a function f, and the other two we'd like to wrap in a function g. So I'm going to use Forest structural search to narrow down the locations we need to wrap in f. However, I'm not going to discuss how that works here. So now we've identified the cursors which contain function calls, and we can leave only these cursors, and now perform the wrapping edit as before. But now we have a problem, because we've lost the other two cursors here that we now need to wrap in G. We could manually solve this by just marking those locations and then performing the edit. But this highlights a problem in Forest. So another way to look at this is if we consider the pseudocode that a refactoring script for this task would have. What's possible in Forest is to check if a location matches a condition, and in that case, perform some edit on it, as we did for f. But afterwards, there must be no further edits on the total set of locations. So what's not possible in Forest is checking a condition, performing an edit on those locations, and then, regardless of the result, performing a different edit on all locations. The other issue I'd like to talk about is the nested copy-paste, which also has its own example. So what we'd like to do here is to take this function expression and change it into an arrow function. So for that, we select the body and copy it. Then we write an arrow function, paste the body, and delete the original function expression. So performing this in one location is possible. But now let's try to do it for both function expressions in this document. So I'll find them quickly. Again, ignoring how I do this. So now notice we have two cursors. We have one where you can see it on the outer function expression, and we have one which you can't see here, but it's on the inner function expression. So these cursors are nested. Now, if we perform the edit the same way as before, we would select the body of the function expression. So notice we have the body of the outer selected, and also simultaneously the body of the inner one. Now we copy the body, we insert the arrow function, and we paste. And now I'd like to show you this intermediate state here. So the inner function expression has been correctly converted to an arrow function. And the outer function expression has also been converted to an arrow function. However, its body still contains the old unconverted function expression. So when we complete this edit by deleting the function expression, we're left with this here, where the outer one was converted, but the inner one still is unconverted. And the issue here is that we performed a copy, and then we performed some further edits, and then pasted, but our pasted nodes did not include our new changes. So the second evaluation we performed, we wanted to understand how often edits occur in practice where a multi-cursor editor would be useful. So for that, we manually inspected all of the commits in Forest codebase and identified edits where we thought multi-cursor could be useful. And we considered a hypothetical text or structural multi-cursor editor for this decision. Importantly, we ignored any edits that came from the rename identifier refactor because we used this refactor extensively in our code base and it always worked perfectly. So we think there's no room for improvement by performing this with a multi-cursor editor instead. However, a multi-cursor editor could, of course, just use this refactor. We then categorized the edits where we thought multi-cursor might be useful. However, we did not attempt to perform them in Forest due to time constraints. So of the 913 commits in the code base, we identified 142, or around 15%, where we thought multi-cursor could be useful. And we investigated half of these further, for which the results are shown here. So in most of these commits, there was one set of edits that had potential to be done with multi-cursor. Some commits also had a couple more unrelated multi-cursor edits. And there were a few commits which had no edits with multi-cursor potential. And these were ones where in the initial evaluation we misjudged and later found that actually no, these edits could not be performed using multi-cursor. So what the second plot shows is an estimated number of cursors that would be used to perform each multi-cursor edit. And as you can see, most edits are performed using a small number of cursors, 2 to 5. Finally, on the right here, we have a table showing the category of each edit which we investigated. I don't have time to explain all of these categories here, but I want to discuss the specialized edit category, since this is the most vague one. So what we mean here are structural edits which are very specific to a given program. Here's an example. So here we see edits in 2 locations. The actual edit was performed in 5 locations, where we're converting this shape of a expression with a function call to this one here. So what we're doing is we're replacing this call to this command handling function by a multi-cursor one. We're changing the way that parameters are passed. So cursors are passed differently. There's this new strict flag. And we're using the multi-cursor helper function instead of the cursors map function. And finally, the way the result is assigned is slightly different in both cases. So as a structural edit, this isn't very complicated. However, it's very specific to the program in which it was performed. And so it couldn't be performed using a built-in refactor in an IDE. And this is the kind of thing that we grouped into the specialized edit category. I'd also like to note that this is one of the more complicated examples in that category. So now to discuss some of the results I've shown. Our evaluation, where we tried to perform the edits of refactoring scripts, highlighted various issues with Forest. And in the written thesis, we've proposed solutions to many of these problems. And additionally, some of these problems are actually ones encountered in other multi-cursor editors, so they've already been solved before. We think, based on the results of this evaluation, that multi-cursor structural editing could replace some, but not all, refactoring scripts. And there might be potential to combine both in a sort of interactive IDE where the user can perform multi-cursor structural edits interactively, but also create and save a permanent kind of script. Our second evaluation showed that edits where multi-cursor could be useful do actually occur in practice. And based on the further discussion that's in the written thesis, however, based on the discussion that's in the written thesis, we think that many of the types of edits that occurred would be an equally good fit for textual or structural multi-cursor edits. Additionally, some of them could be performed with refactors. And for some of these edits, we think there are interesting new refactors which could be designed. However, there were also some edits which we think would be best performed with a multi-cursor structural editor. And these are mainly the ones in the specialized edit category. So to conclude, we built Forest, the only structural editor that specially integrates multi-cursor features. We think that Forest can be an interactive alternative to some, but not all, refactoring scripts based on the results of our evaluation, where Forest could perform 11 out of the 48 edits from real-world refactoring scripts. And we think that by fixing certain issues and features we've identified during this evaluation, it could perform the edits of 17 more scripts well. Additionally, our second evaluation showed that multi-cursor edits do occur in practice. We found potential for them in around 15% of real-world commits. And we think there are some of these edits where a structural multi-cursor editor is the best fit. So in around 1/3 of the commits. Okay, that's it.